Hello everybody and welcome to my 29th video. This is on a design method for the maximum of, minimum of and difference of gates. The circuit diagrams for these can be found in my 5th video, Binary Implemented Ternary Logic Circuits, and my 25th video, Binary Implemented Quaternary Logic Circuits. This is a design method whereby you don't have to design it using a counter map. It's an automatic formula for doing it. Okay, so let's get started. Here we have a Boolean operator. W subscript n equals 1 if and only if w is greater or equal to n and 0 otherwise. Like I said, wn is a Boolean unary operator. And these are values which n can assume. N equals 1 to r minus 1 and w is a member of 0, 1 to r minus 1. So I have a few examples here of wn, the Boolean operator. Here in the binary case, w equals 0, 1, w1 equals 0, 1, which is the same as w. In the ternary case, w equals 0, 1, 2. This is W1 and this is W2, and in the quaternary case 0, 1, 2, 3, this is W1, this is W2, this is W3. So for R equals 2, W1 equals W, which can be seen here, and for any radix 0 to the n equals 0 and R minus 1 to the n equals 1. Here we have 0, 0 to the 1 equals 0, R minus 1 here is 1, because the radix is 2, that's 1, r minus 1 equals 1. Here for ternary, r equals 3, r minus 1 is 2, so that's a 1 in all cases. This 0 here is a 0 in all cases, and for r equals 4 quaternary, you've got r minus 1 here is 3, so that's a 1 in every case, and here 0 is a 0 in every case. N equals 1, 2 and 3. Okay. So here we're going to do the minimum of gate. First of all, we're going to let f of a to the x comma b to the y equals minimum of a and b to the z. Now where x, y and z equals 1 to r minus 1 and AB is a member of 0, 1 to r minus 1. So first we let r equal 2, which is binary. So in the binary case, the minimum of function min AB equals a and b. So we're going to substitute this into here. So 1.1 into 1.0 into there. So we have f a to the 1, b to the 1 equals a and b to the 1. Now in the binary case w1 equals w, as I've said earlier. Therefore f a b equals a and b. So there we're going to let f a to the x b to the y equals a to the x and b to the y. So these are Boolean value variables, and we're dealing with a Boolean equation, so this is valid. So now we're going to substitute 1.2 into 1.0. This is 1.2, 1.0, and we get min AB to the z here equals a x to x and b to the y, which is there. So now we're going to let b equal r minus 1, or min a r minus 1 to the z equals a to the x and r minus 1 to the y. R minus 1 to the y equals 1, therefore min a r to the r minus 1 to the z equals a to the x and 1. So this equals a and this equals a here. So we have a to the z equal a to the x. Therefore z equals x, because the subscripts must be the same. Now we let a equal r minus 1, same procedure, min r minus 1 b to the z equals r minus 1x and b to the y. R minus 1 to the x equals 1, therefore min r minus 1 b to the z equals 1 and b to the y. Therefore conclude that b to the z equals b to the y. Therefore z equals y. The subscript must be the same. So we conclude that x equals y equals z, therefore minimum of a and b to the z equals a to the z and b to the z. Right. Next we're going to deal with the Maximov gate. It's a similar procedure as with the Minimov gate. So we let f a to the x of b to the y equals max a b to the z. And again x, y, z equal member of 1, 2, r minus 1. A and b are members of 0, 1, 2, r minus 1. So we let r equal 2, which is binary. In this case, the maximum function max a b equals a or b. Substitute 1.2 into 2.0. That's 1.0. 2.1. That's 2.0. We have f a to the 1, b to the 1 equals a or b to the 1. W1 equals w because we're dealing with binary. Therefore, fab equals a or b. And therefore, f a to the x and b to the y equals a to the x or b to the y. So these again are binary variables and we're dealing with the binary r equals 2. So now we let r be greater than 2, substitute 2.2 into 2.0, so we get max ab equals a to the x or b to the y. Now we let b equals 0, so max a and 0 z equals a to the x or 0 to the y. 0 to the y equals 0, therefore max a comma 0 to the z equals a to the x or 0, and max a to the a or 0 equals a to the x or 0 equals a to the x, therefore we conclude that a to the z equals a to the x, therefore z equals x. Now we'll let a equals 0, max 0 comma b to the z equals 0 to the x or b to the y. 0 to the x equals 0, therefore max 0 comma b to the z equals 0 or b to the y. Now this equals b to the z and so does this equals b to the y. So we conclude that z and y are the same, z equals y. Therefore x equals y equals z, therefore max a b to the z equals a to the z or b to the z. Right. I must say that these are multiple variable functions. So a maximum function of a, b, c, for example, would be a to the z, b to the z, c to the z, etc. So what you do is you leave a alone and set all the other inputs to 0 and you get that result. Then you leave b alone and set all the other inputs to 0 and you get this result. Then you would leave, say, c, for example, alone and set all the inputs to 0 and get a to the z or b to the z or c to the z. So it's a multiple values of function. Okay, and that applies to the Minimov gate as well, where you would set all the inputs to r minus 1 and leave one variable alone. And that would be min a b z equals a z and b z on c z, for example, for 3 variables. So now we're going to deal with the difference of gate. So again, we're going to let f a to the x and b to the y equals difference a b to the z. X and y are members of 0 to r minus 1. AB is a member of 0, 1 to r minus 1. And so we'll let r equal 2, so we're dealing with binary. In this case, the difference gate AB equals A exclusive or B. So we substitute 3.1 into 3.0 there, and we get F A to the 1, B to the 1 equals A exclusive or B to the 1. Now we're dealing with binary, so W1 equals W, therefore FAB equals A exclusive or B. Therefore, f of a to the x comma b to the y equals a to the x exclusive or b to the y. Because we're dealing with, these are Boolean operators, and we're dealing with Boolean algebra because r equals 2. So now we'll let r be greater than 2, so ternary, quaternary, etc. So substitute 3.2 into 3.0 into here, and we get the difference ABZ equals a to the x exclusive or b to the y. So now we're going to let b equals 0, difference of a and 0 to the z equals a to the x exclusive or 0 to the y. 0 to the y equals 0, therefore the difference of a and 0 to z equals a to the x exclusive or 0. Now this equals a, and so a to the x exclusive or 0 equals a to the x. So we conclude that a to the z equals a to the x, therefore z equals x. So now we'll let a equals 0, difference of 0 and b to the z equals 0 to the x exclusive or b to the y. 0 to the x equals 0, therefore difference of a 0 comma b to the z equals 0 exclusive or b to the y. So this equals this equals b, and 0 exclusive or b to the y equals b to the y. Therefore b to the z equals b to the y. So we can conclude that these subscripts are the same, therefore z equals y. Therefore x equals y equals z. Therefore the difference of a, b to the z equals a to z exclusive or b to the z. Now this is a 2-input function only, so it doesn't apply to a multiple amount of variables. It's only a 2-variable function. Okay. So to summarise, min of xo, x1 all the way to the xm to the n equals xo to the n, x1 to the n all the way to xm to the n. So it applies for any amount of variables. I've just replaced xo, x1, xm with a, b, c, etc. Same for the maximum function, the max xo, x1 all the way to the xm to the n equals xo to the n, x1 to the n, all the way up to xm to the 1, or connected together by the or function, xm to the n. And the difference of function, difference of xo and x1 to the n equals xo to the n exclusive of x1 to the n, where n equals 1, 2 to the n minus 1, xo, x1, xm members of 0, 1 to all the way to r minus 1. Right, well, I think that concludes the video. I'd just like to say I hope you've enjoyed it. Thanks for watching. Bye.